Welcome to this coding walkthrough. Today, we'll be diving into problem number 852, peak index in a mountain array. This is a fascinating problem where we explore efficient ways to find the peak element in a mountain-shaped array. Let's break it down step by step and uncover the best solution. In this problem, we are working with a special type of array called a mountain array. A mountain array has a specific structure. It starts with a strictly increasing sequence of integers, reaches a peak, and then transitions into a strictly decreasing sequence. For example, consider an array where the elements climb upward, reach their highest value at some index, and then descend. The task here is to find the index of that peak element, which is the largest value in the array and lies at the point where the increasing sequence switches to decreasing. The problem guarantees that the input array will always follow this mountain array structure. The input array, RR, has a length of at least 3 and can go up to 10,000 elements, with values ranging from 0 to 1 million. Your output will be a single integer representing the index of this peak element. To understand this better, let's look at some examples. In the first example, the input array is 0, 1, 0. Here, the array starts with an increasing sequence, 0, 1, and then transitions into a decreasing sequence, 1, 0. The peak element is 1, which is the largest value in the array, and it occurs at index 1. Thus, the output for this input is 1. This demonstrates the basic structure of a mountain array and how we identify the peak index. Now, consider another example where the input array is 0, 2, 1, 0. In this second example, the array 0, 2, 1, 0 also follows the mountain array properties. The increasing sequence is 0, 2, and the decreasing sequence is 2, 1, 0. The peak element is 2, which is the largest value in the array, and it is found at index 1. Therefore, the output here is also 1. Let's examine one more example to further solidify our understanding. Consider the input array 0, 10, 5, 2. In this final example, the array 0, 10, 5, 2 satisfies the mountain array conditions as well. The increasing sequence is 0, 10, and the decreasing sequence is 10, 5, 2. The peak element is 10, which is the largest value, and it occurs at index 1. Therefore, the output is 1. Now, let's look at some additional constraints and edge cases. The array length will always be at least 3 and at most 10, 0, 0, 0, and each element is guaranteed to be within the range of 0 to 1, 0, 0, 0, 0, 0, 0. A few edge cases include the smallest possible mountain array, such as 1, 3, 2, where the peak is at index 1, or a peak occurring close to either end of the array, such as in 2, 3, 4, 5, 6, 7, 6, where the peak is at index 5. These constraints ensure the problem is well defined and that we can always identify the peak index. To solve the problem of finding the peak index in a mountain array, we considered two main approaches. The first is the brute force approach, which relies on a straightforward intuition. By iterating through the array, we can compare each element with its neighbors to check if it's greater than both. If it is, that index is the peak. The algorithm for this method involves traversing the array from the second element to the second to last element and checking the peak condition at each step. While this approach is simple and requires no additional data structures, it has a major drawback: its time complexity is O(n). This means that for large arrays, it can become inefficient as it inspects every element until the peak is found. Alternatively, we explored the binary search approach, which leverages the unique structure of a mountain array. Here, we take advantage of the strictly increasing sequence followed by a strictly decreasing sequence. The key observation is that if the element at the middle index is smaller than the next element, the peak must be on the right. Conversely, if the middle element is greater than the next, the peak will be on the left or at the middle index itself. This insight allows us to narrow down the search space significantly compared to the brute force method. The binary search algorithm begins by initializing two pointers, low and high, to the start and end of the array, respectively. We then repeatedly calculate the middle index using the formula mid equals low plus high ///2. If the element at mid is smaller than the element at mid plus 1, it indicates we are in the increasing portion of the mountain, so we adjust low to mid plus 1 to focus on the right half. Otherwise, we adjust high to mid, as the peak must be on the left half or at mid itself. This process continues until the pointers low and high converge, at which point the peak index is found at low. The binary search approach is highly efficient, with a time complexity of O log n, since the search space is halved in each iteration. Additionally, it has a space complexity of O(1), as it doesn't require any extra memory. This efficiency makes it ideal for large arrays. The downside, however, is that it is slightly more complex to implement than the brute force method, though the performance benefits far outweigh this added complexity. While considering alternative approaches, we explored two other options. The first was a recursive implementation of binary search, which mirrors the iterative version but uses function calls to divide the search space. However, this recursive method offers no real advantage over the iterative approach and could introduce additional overhead due to stack usage. Another alternative was a divide-and-conquer strategy, which involves splitting the array recursively to locate the peak. While theoretically interesting, this approach has higher implementation complexity and does not improve upon the efficiency of binary search. After evaluating these options, we concluded that the iterative binary search approach is the optimal solution. It aligns perfectly with the problem structure, taking advantage of the unique increasing then decreasing pattern of the mountain array. The logarithmic time complexity of binary search ensures scalability, and its simplicity compared to recursive alternatives makes it a practical choice. Although it is slightly more complex to implement than brute force, the performance improvements justify this trade-off. The key insight that unlocked the binary search approach was recognizing that the relative comparison between ARR mid and ARR mid plus 1 reveals the slope direction. This simple yet powerful observation allowed us to systematically narrow down the search space and pinpoint the peak index efficiently. After weighing all options, we chose the iterative binary search method as our final solution. It strikes the perfect balance between efficiency, simplicity, and scalability. By leveraging the problem's inherent structure, this approach not only ensures optimal performance but also avoids the overhead of recursion or the inefficiency of linear scans. This combination of advantages makes iterative binary search the clear choice for solving the peak index problem in a mountain array. To begin solving the problem of finding the peak index in a mountain array, let's break it into clear steps. First, we need to understand what a mountain array is. It's an array where the elements increase to a single peak and then strictly decrease afterward. For example, in the array 1, 3, 5, 7, 6, 4, 2, the peak is 7 at index 3, because it's greater than its neighbors. Next, we initialize the process by confirming that the input array, ARR, has at least 3 elements. This is important because a valid mountain array requires a minimum of 3 elements to form both an increasing and a decreasing sequence. Once that's checked, we plan our iteration. The iteration starts from index 1, the second element, and goes up to ARR length 2, which is the second to last element. This is because the peak cannot occur at the first or last index. The strictly increasing and decreasing nature of the array makes it impossible for boundary elements to be peaks. Now, let's define how to identify a peak during the iteration. At each index I, we check 2 conditions. First, is the current element ARR I greater than the previous element ARR I1? And second, is ARR I greater than the next element ARR I plus 1? If both conditions are satisfied, then I is the peak index, and we can return it immediately. This ensures that as soon as we locate the peak, we stop further computation. If no peak is found, though this is guaranteed to happen in a valid mountain array, we would return -1. Lastly, we also need to address some edge cases. For example, if the array has fewer than 3 elements, it's not valid, and we should return -1. Similarly, peaks cannot occur at the boundaries of a valid mountain array, so we don't check these indices. This setup ensures that all scenarios are properly handled. Now, let's understand the key insights behind this approach. We compare each element to its neighbors because a peak is strictly greater than both its adjacent elements. This simple comparison helps us confirm whether the current index satisfies the peak condition. The iteration is limited to indices between 1 and n2 because, in a valid mountain array, the first and last elements cannot be peaks. This saves us from performing unnecessary checks at those boundaries. In terms of efficiency, this brute force approach is linear with a time complexity of O(n), where n is the length of the array. Each element within the valid range is checked exactly once, making the method straightforward and efficient for many practical cases. The implementation of this solution relies on basic data structures. Specifically, the input is simply an array, and no additional data structures are required. This is because the problem only involves comparing adjacent elements to determine whether a peak exists. While the brute force approach is efficient in its simplicity, there is room for optimization if we need to handle very large arrays. By using a binary search approach, we can reduce the time complexity from O(n) to O log n. This is possible because the mountain array's nature, first increasing and then decreasing, allows us to apply binary search to locate the peak more efficiently. This makes the binary search approach an excellent alternative for scenarios where performance is a critical factor. Let's solidify our understanding with an example. Consider the array ARR equals 2, 4, 6, 8, 7, 5, 1. First, we validate the input. Since the array length is 7, which is greater than or equal to 3, it's a valid mountain array. Now, we start iterating from index 1, which has a value of 4. We check if 4, 2 and 4, 6. The first condition is true, but the second is false, so we move to the next index. At index 2, the value is 6. We check if 6, 4 and 6, 8. Again, the first condition is true, but the second is false. Finally, at index 3, the value is 8. We check if 8, 6 and 8, 7, and both conditions are true. This confirms that index 3 is the peak. We return 3 as the output, demonstrating how the algorithm correctly identifies the peak through systematic iteration and comparisons. The above code implements an efficient binary search solution for finding the peak index in a mountain array. The problem guarantees that the array is a valid mountain, meaning it increases to a peak and then decreases. The goal is to return the index of the peak element. Step-by-step explanation. 1. Initialization. 2 pointers left and right are initialized to the start, 0, and end, length of the array -1, of the input array ARR. 2. Binary search loop. The loop continues as long as left is less than right. This ensures the search space is reduced until we converge on the peak index. 3. Calculate midpoint. The midpoint mid is calculated using integer division, left plus right, //2. 4. Comparison to determine search direction. If ARR mid is less than ARR mid plus 1, it means we are on the increasing slope of the mountain. The peak lies to the right of mid, so we move the left pointer to mid plus 1. Otherwise, if ARR mid is greater than or equal to ARR mid plus 1, it means we are on the decreasing slope or at the peak. In this case, we move the right pointer to mid. 5. Convergence to peak. Eventually, the left and right pointers will converge to the same index, which is the peak index. At this point, we return left or right as they are equal. Key insights. The binary search approach reduces the time complexity to O log n, which is highly efficient compared to a linear scan O(n). By comparing ARR mid with RR mid plus 1, we effectively decide which side of the array contains the peak. The algorithm works because the array is guaranteed to be a mountain, so there is always one peak. Edge case handling. The problem guarantees that the input is a valid mountain array with at least 3 elements, so no additional checks for invalid input are required. This solution is optimal, concise, and leverages the properties of a mountain array to achieve logarithmic time complexity. This is the Java implementation of LeetCode problem number 852, peak index in a mountain array. The solution uses the binary search approach, similar to the provided Python solution. Key differences include Java's explicit type declarations and the absence of Python-specific syntax. The algorithm ensures O log n time complexity by narrowing the search space based on the comparison between the mid and mid plus 1 elements. To begin solving the problem, we start with the array 0, 2, 4, 6, 5, 3, 1. Our goal is to find the index where the peak of the mountain lies, which is the largest value in the array. Initially, we set left to 0 and right to 6, representing the bounds of the array. In the first iteration, we calculate the middle index using left plus right //2, which gives us mid equals 3. At this point, we compare the value at mid, which is 6, with the value at mid plus 1, which is 5. Since 6 is greater than 5, we know the peak lies on the left side of the array, or possibly at mid. Therefore, we update right to mid, making it 3. Next, in the second iteration, we recalculate mid as left plus right, // 2, resulting in mid equals 1. Now, we compare ARR mid, which is 2, with ARR mid plus 1, which is 4. Since 2 is less than 4, the peak must lie on the right side. We then update left to mid plus 1, making it 2. In the third iteration, we again recalculate mid as left plus right, // 2, which gives us mid equals 2. At this point, we compare ARR mid, which is 4, with ARR mid plus 1, which is 6. Since 4 is less than 6, we conclude that the peak is on the right side. This means we update left to mid plus 1, setting it to 3. Now, both left and right are equal to 3, which causes the loop to terminate. At this point, we return left as the peak index. The value at index 3 is indeed the peak, as 6 is the largest number in the array. Let's now consider a second example with the input array 1, 3, 5, 6, 4, 2. Again, our task is to find the peak index. Initially, we set left to 0 and right to 5. In the first iteration, we calculate mid as left plus right, // 2, which gives us mid equals 2. We then compare ARR mid, which is 5, with ARR mid plus 1, which is 6. Since 5 is less than 6, the peak must lie on the right side. Therefore, we update left to mid plus 1, making it 3. In the second iteration, we recalculate mid as left plus right, // 2, resulting in mid equals 4. Here, we compare ARR mid, which is 4, with ARR mid plus 1, which is 2. Since 4 is greater than 2, the peak lies on the left side, or possibly at mid. Thus, we update right to mid, setting it to 4. In the third iteration, we calculate mid as left plus right, // 2, which gives us mid equals 3. We then compare ARR mid, which is 6, with ARR mid plus 1, which is 4. Since 6 is greater than 4, we conclude that the peak lies on the left side, or possibly at mid. As a result, we update right to mid, making it 3. At this point, left and right are both equal to 3, so the loop terminates. We return left as the peak index. In this case, the value at index 3 is 6, which is the peak of the array. Now, let's examine a third example with the input array 3, 4, 5, 3, 2, 1. Starting off, we set left to 0 and right to 5. In the first iteration, we calculate mid as left plus right, // 2, which gives us mid equals 2. We then compare ARR mid, which is 5, with ARR mid plus 1, which is 3. Since 5 is greater than 3, the peak lies on the left side, or possibly at mid. This leads us to update right to mid, making it 2. In the second iteration, we recalculate mid as left plus right, // 2, resulting in mid equals 1. At this point, we compare ARR mid, which is 4, with ARR mid plus 1, which is 5. Since 4 is less than 5, we know the peak must lie on the right side. Therefore, we update left to mid plus 1, setting it to 2. Finally, we reach the state where left is equal to 2 and right is also equal to 2. Since left and right are the same, the loop exits. At this point, we return left as the peak index. In this array, the value at index 2 is 5, which is the largest value and therefore the peak. This concludes our third example, demonstrating the use of binary search to efficiently find the peak index in a mountain array. To analyze the time complexity of this algorithm, we start with the initialization of the pointers. The variables left and right are set to the beginning and end of the array, respectively. This is a straightforward operation and takes constant time, or O1. Next, we focus on the binary search loop, which is the core of the algorithm. In this loop, we repeatedly calculate the middle index, mid, and compare the value at ARR mid with ARR mid plus 1. Both of these operations, finding the middle and performing the comparison, also take O1 time. The key insight here is that the binary search approach reduces the search space by half in every iteration. Given that having the search space continues until only one element remains, the number of iterations is proportional to the logarithm of the array size, specifically log base 2 of n. This makes the total time spent inside the loop O log n. Finally, when the loop ends, the algorithm returns the value of left or right, which is another O(1) operation. Combining all these steps, the overall time complexity of the algorithm is O log n. Now let's examine the space complexity. The algorithm operates directly on the input array ARR without creating any additional copies of the array. This means the space required for the input is O(n), but this doesn't contribute to the auxiliary space complexity. Instead, we focus on the auxiliary variables used in the algorithm. These include left, right, and mid, all of which require a constant amount of space. Since no other data structures or recursive calls are used, the auxiliary space complexity is O(1). When we combine these considerations, the total space complexity of the algorithm is O(1), as input size is not factored into auxiliary space calculations. Let's compare this approach to a brute force method. A naive solution would involve iterating through the entire array and comparing each element with its neighbors to determine the peak index. For an array of size n, this approach could require up to n comparisons in the worst case, resulting in a time complexity of O(n). However, the space complexity remains O(1), as no extra memory is allocated. In contrast, the binary search approach offers a significant improvement in time complexity. By leveraging the sorted nature of the mountain array, we narrow the search space in logarithmic steps, reducing the time complexity to O log n. The space complexity remains O(1), as no additional memory structures are needed. This makes the optimized approach both faster and more efficient, especially for larger arrays. To solidify our understanding of the time complexity, let's provide a mathematical proof. In binary search, the search space is halved at each step. Initially, the search space is the entire array of size n. After the first iteration, the search space is reduced to n/2. In the next iteration, it's n/4, and so on. After k iterations, the search space becomes n divided by 2 raised to the power of k. The loop exits when the search space is reduced to 1, which gives us the equation n/2 to the power of k equals 1. Solving for k, we find that k equals log base 2 of n. This confirms that the number of iterations, and therefore the time complexity, is O log n. As for space complexity, the algorithm uses only a constant amount of memory for variables like left, right, and mid. Since no additional memory is allocated beyond this, the space complexity is O(1). When solving the peak index in a mountain array problem, there are a few common mistakes to watch out for. First, it's essential to handle edge cases properly. A valid mountain array requires at least 3 elements, one peak with strictly increasing values on the left and strictly decreasing values on the right. Failing to validate this constraint could lead to runtime errors or incorrect results. Another mistake is assuming that the array is always strictly increasing or decreasing. For example, arrays like 3, 2, 1, or 1, 2, 3 are not valid mountain arrays, so solutions making this assumption will fail. Boundary errors during comparisons are also frequent, especially when accessing neighbors like ARR I1 or ARR I+1. Always ensure that the index is within bounds before performing these operations. Lastly, some solutions unnecessarily include linear search within optimized algorithms like binary search, which undermines the efficiency of the logarithmic approach. Avoid mixing these strategies to maintain optimal performance. Another common pitfall is misunderstanding the mountain property itself. For the array to qualify as a mountain, it must strictly increase on one side of the peak and strictly decrease on the other. That means conditions like ARR I1 for the left slope and ARR I+1 for the right slope must hold true. Moving on to interview insights, one key takeaway is that this problem boils down to identifying the maximum in a unimodal array. This property is what allows binary search to work so efficiently here. It's also valuable to recognize patterns. For example, problems involving peaks or local extrema often benefit from divide and conquer strategies like binary search. Interviewers may test your understanding of the constraints, so you should be prepared to identify and handle invalid inputs, such as arrays that don't meet the mountain criteria. Lastly, while the brute force approach is easier to grasp, it comes with an O(n) time complexity, which is less efficient for large datasets. Binary search, by contrast, reduces the complexity to O log n, making it the superior choice in most cases. This problem is closely related to several others on LeetCode that also emphasize peaks in binary search. For example, LeetCode 852 focuses on finding the index of the peak in a mountain array, which is essentially the same as this problem. LeetCode 162 generalizes this idea, asking you to find a peak in any array, not necessarily a mountain array. Then there's LeetCode 35, which highlights the mechanics of binary search, helping you refine the logic used to narrow down search spaces. LeetCode 1095 is another interesting variation that combines peak finding with binary search on both sides of the peak, adding complexity to the problem. In terms of approaches, the brute force method involves iterating through the array and comparing each element with its neighbors. While easy to implement, it has a time complexity of O(n), making it less suitable for larger inputs. On the other hand, the binary search approach uses the mountain property to efficiently narrow down the search space. By checking whether you're on the increasing or decreasing slope, you can converge on the peak in O log n time. This approach requires more thought, but it delivers a significant performance advantage. A less common alternative to binary search is the two-pointers approach. Here, you place one pointer at the start of the array and another at the end, then move them inward simultaneously, one traversing the increasing slope and the other the decreasing slope. While this method is easier to implement than binary search, its time complexity is still O(n), making it less efficient for interviews or large datasets. As a result, this approach is generally not the preferred choice, but it's worth understanding as another way to think about the problem, especially if you're brainstorming solutions during a time setting or trying to build intuition about mountain arrays. Ultimately, binary search remains the gold standard for this problem due to its efficiency and alignment with the problem's constraints. Great job following along. In summary, we tackled finding the peak index in a mountain array, starting with a brute force approach and optimizing to a more efficient solution using binary search. Remember, problems like these are excellent practice for understanding both algorithmic efficiency and problem-solving strategies. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!